In this lecture, we'll discuss the radiation heat transfer between the two bodies which have opaque, diffuse, gray and isothermal. So while calculating the heat transfer from radiation, we'll consider that the surface are opaque, diffuse, gray and the surface are considered as isothermal. In addition to this, opaque surface means that the value of transmissivity tau equals to 0. Or we can say that alpha plus rho equals to 1 minus alpha. And it is also known that for alpha is same as emissivity. So we can write that rho equals to 1 minus epsilon. Now consider here any body, and on this one there is a incident radiation equals to G. As the irradiation fall on the body, some of the energy get reflected. That amount will be equals to rho times G, and some amount of energy is absorbed. Nothing is transmitted because our value of tau equals to 0 and assumption is opaque. So because of this, the temperature of the body will increase and it also start emitting depending upon the value of emissivity epsilon, the EB. As we considered gray body, we have a certain emissivity. So total amount of quantity that was emitted from this one, that equals to rho into G plus epsilon into EB. So this total sum is called as radiosity. Radiosity is represented by J. So we have J equals to rho times G plus epsilon multiplied by emissive black power of the black body. But rho is equals to same as 1 minus epsilon from this equation multiplied by G plus epsilon multiplied by EB. From the equation we can find out that J minus epsilon multiplied by EB is same as 1 minus epsilon multiplied by G, that is irradiation. So we can solve for radiation as G equals to J minus epsilon into EB divided by 1 minus epsilon. The net amount of energy incident upon the body is equals to J and the leaving quantity equals to J. So net amount leaving the surface, that is equals to Q, will be equals to J minus G. So this equals to J minus of epsilon into EB upon 1 minus epsilon. So if we cross multiply and we can solve this for 1 minus epsilon. So this quantity is get multiplied as J is minus of epsilon multiplied by J minus of J minus is plus epsilon multiplied by EB. So here this J and minus J is cancelled. So what is left is epsilon multiplied by EB minus of epsilon multiplied by J is 1 minus epsilon. Now this quantity can also be written as epsilon is a common quantity. So we left with EB minus J upon 1 minus epsilon. In a resistance language, we can write this term as EB minus J upon 1 minus epsilon upon epsilon. The denominator of this term is called as resistance and is called as surface resistance. If the body is a black surface, epsilon is 0 and therefore for black surface there is no surface resistance. Only in the case of gray surface we have the surface resistance. This resistance can be shown for body number 1, and if we have a body number 1 at temperature equals to T1 and having emissivity equals to epsilon 1, so the emissive power of this body is EB, which is given as sigma multiplied by T to the power 4, and from this we have a resistance called as surface resistance, and this one is radiosity J1, this one is EB1, and the surface resistance in this case is given by 1 minus epsilon upon epsilon. This quantity that is coming net from this is heat transfer divided by unit area, that one is watts per meter square. Now let's consider there is another body, body number 2, at temperature equals to T2 and emissivity equals to epsilon 2, and only two bodies take part in the heat transfer. So amount of emissive power of this body is EB2, which is same as sigma into T2 to the power 4. This one is T1 to the power 4. And when the radiation from this will go to the body number 2, it has a surface resistance. So in this case, this is 1 minus epsilon 2 upon epsilon 2. And in this case, this value will be 1 minus epsilon 1 divided by epsilon 1. And from this one, we have J2 as a radiosity. So in between these two, so radiation coming from this side, the total quantity Q coming from this side is A1 multiplied by, so that it can be written as shape factor F12. Only this part will reach by body number 2. And from this side we have F21. So how much part of body number 2, body number 1 you can see from body number 2, according to that it will reach. So net radiation reaching to the body number 1 is A1 J1 F12 minus A2 J2 F21. So net heat transfer is A1 F12 J1 minus of A2 F21 J2. But we also know that according to reciprocity rule, A1 F12 is same as A2 F21. So we can take out A1 F12 common, and what we left is simply common quantity is J1 minus J2. Again, in the resistance way, we can write this quantity as J1 minus J2 divided by 1 upon A1 F12. Now this resistance is called as the surface resistance. So this resistance we have to add. This one is given as 1 upon A1 F12. So total there are three resistances. This resistance is called as surface resistance. This one is called as space resistance, and we have surface resistance. We have two surfaces, we have two surface resistance, and between them one space resistance. So whenever the heat is transferred from body number 1 to body number 2, it encountered three types of resistances. One is surface for surface 1, second is also surface for surface 2, and in between this we have a space resistance.